Yeah, can you see it full screen? Does it look nice?
Yes. Yeah.
Okay, perfect. So, all right, so let's get started. First of all, thank you very much for the invitation. It's a pleasure to talk to you this morning there and this evening in Toronto. And thank you very much, for joining us this morning. Today, I will talk about sequential decision-making under uncertainty and tell you guys a little bit about the specific policies that we propose. We are calling Lagrangian dual decision rules, and the name will be clear hopefully as we go shortly. I will try to fit it into this 45 minutes or so, but please feel free to interrupt me at any point. So if you want me to explain any concept further. So I know that there's a lot of optimization going on there in Optima. I checked some of your research projects, so I hope many of you will be familiar, but in case you are missing some background or you want to hear more about the details, or if you want to jump in and ask any questions, feel free to interrupt me at any time during the talk via the chat screen, or just unmute yourselves and ask the question directly. All right, so what is sequential decision making under uncertainty? So as the name suggests, we would like to make a sequence of decisions, most important ones being the ones to be made at stage one. So we divided our planning horizon to, let's say, a finite number of decision stages. At each one of them, we have a vector of decisions to be made. But that's not all about it, about the setup. We also have this uncertainty that impacts our whole system. And this uncertainty is gradually revealed to us over this planning horizon. So we are supposed to make our, let's say, stage t-1 decisions, and then we observe a new set of random variable observations. Uncertainty is revealed to us, and we continue with our next stage t decisions. And in that regard, in this sequential decision-making under uncertainty framework, we need to be able to adapt our decisions based on what we observed with respect to the uncertainty already, as well as, of course, our previously committed decisions. According to both of these concepts, we are going to make our next set of decisions. And sequential decision making under uncertainty has a variety of applications in a variety of fields. I would like to, if the time permits, will tell you guys about like 4 different application domains where we will apply these new decision rules that we are proposing. So first of which is this production planning problem, which I will also use throughout my talk as a running example. So this is a bit everyone is familiar with. You have a bunch of products that you are hoping to make a production plan, again, over a finite set of decision stages, and accordingly you need to observe the uncertain demand for each of these types of products that you care about, and then according to the demand realizations and your production levels, you can either adjust your schedule, or more so you must be just doing this inventory management as you go. And another example, I know some of you have been working on call center related operations in Optima, is again the scheduling problem, but this time in other service system. For instance, in call centers, what we need to do is we need to define for each type of agents that you might have in your system, you might need to decide on how many of these agents you might want to have, the staffing levels, as well as their associated schedules you need to decide. But in the course of the planning horizon, the demand will be the main source of uncertainty, which will be revealed to you. The calls will come in via a stochastic process, according to which you need to assign these upcoming demand of calls to your available agents and update the queues, whatnot. Another example will come from healthcare domain, and if time permits, I will tell you a little bit about these operating room scheduling problem, where the surgery durations will be the main source of uncertainty, and we need to adapt our scheduling decisions according to the random observations. And final example would be for this novel application that we have done recently on telecommunications area, where we are trying to solve a resource allocation problem. Again, there the demand will be the main source of uncertainty, and our resource usages and according to how we meet the demand need to be adapted towards what we observed in terms of uncertainty as well as our prior decisions. So if you have such a sequential decision making under uncertainty, you can follow a variety of modeling frameworks, 2 of which we will be focusing on today, especially the first one, stochastic programming. So the main assumption of stochastic programming as a modeling framework is the fact that for our random variables, random quantities in the system, we have an idea about their underlying true probability distribution. This is the main assumption, in which case, depending upon how many decision stages you have in your problem, in your model rather, we have these 2 important studied problem classes, 2-stage stochastic programming, and if you have multiple decision stages, I will give you more details about their setup shortly. We will talk about the multi-stage stochastic programming. And in fact, in our work, we will be focusing on a very, very challenging problem class, namely multi-stage stochastic programming, where we also have some integer valued decisions. So we will be looking into mixed integer programming version of multi-stage stochastic programs. On the other hand, if you don't necessarily have this underlying probability distribution information about the underlying stochastic process regarding your uncertain parameters, then you might want to follow a robust optimization approach. Or regardless, maybe if you want to take a little bit of a more pessimistic approach in terms of decision making, again, robust optimization will help you in that regard. So again, in terms of whether you can adapt your decisions towards the observations of the uncertainty, if you won't be able to do that, then you are talking about static robust optimization models. On the other hand, if you will be able to adjust your decisions as you go, then we are talking about adaptive robust optimization ARO. And our main goal will be, again, one of the most challenging class of robust optimization problems, namely multi-stage adaptive mixed integer robust optimization problems, MSARO. So the big picture, we have these two modeling frameworks for sequential decision-making under uncertainty, either multi-stage stochastic programming or multi-stage adaptive robust optimization. For both of those, we will propose these so-called Lagrangian dual decision rules, and they are basically going to tell us, they will be policies, and they will tell us what to do at any point of the time given the system state. So these rules will tell us what type of decisions to be made and accordingly what to set their values to. And this new policies that we are aiming for, that will actually allow us to develop some novel methodologies, but I won't probably have much time to get into their details, but I will try to give you a little bit of an idea how the general methodologies work. And in that regard, as much as time permits today, I will tell you a little bit about applications of those from a variety of areas. So before I get into any details, let me just tell you the key idea. We are looking at these very challenging multi-stage problem classes. So these are like notoriously difficult to solve, both theoretically as well as computationally. So let's simplify them. On the other hand, compared to the multi-stage, so by the way, I will start annotating my slides so I cannot hide my color scale, you will be seeing it. So in that regard, like if you look at the literature for both stochastic programming and robust optimization, if you only focus on two-stage versions of these models, then there exists a variety of like very, very efficient solution methodologies, or at least we can solve two-stage versions of this problem much, much better than multi-stage versions. That's where our key idea will come into play. We will design some policies that will collapse these multi-stage problems into two-stage ones, and whatever nice methodologies we have available there, we will be able to leverage them in regards to developing solutions to these restricted problems. Okay, so I will start with the stochastic programming version. So I will tell you our ideas, these so-called Lagrangian dual decision rules for multi-stage mixed integer programming models. But as I said, the key idea would be collapsing these multi-stage models into two-stage ones. So let me tell you briefly in one slide what two-stage stochastic programs are. So as the name suggests, we do have some stochastic components. In other words, we do have some uncertain parameters in our model where we are modeling them via random variables. In other words, the main assumption of stochastic programming comes into play. We assume that we know their joint probability distribution. In terms of the decision stages, as the name suggests, we get to make decisions 2 times. So we can only adapt after observing the random variable realizations only once. So in that regard, we do have these first stage decisions to be made before having any idea about these realizations of the random variables. For instance, if you are trying to make a production plan, then in our random variables will be, let's say, demands of the products, and we will need to make our production plan and fix it before having observed the actual demand realizations. And in that regard, whatever the production plan you set in the first stage, then you will incur a first stage immediate cost. On the other hand, after observing these realizations, the demands, then we can make a second set of decisions. Maybe if we are short of meeting certain types of products demands, we can outsource them, or we can maybe produce last minute a bit more, we can do overtime. So you can make this further set of decisions called second stage or recourse decisions. But these decisions, of course, the second stage decisions, they do depend on these random variable realizations. So the second stage cost in the most traditional way of stochastic programming, we need to minimize their cost in the expected form. So the commonly used objective in stochastic programming is minimizing this deterministic first stage cost plus expected second stage cost, where this expectation is taken with respect to the distribution of the random variables, let's say demands. So let's extend this to the multi-stage setting. So instead of the 2 decision stages, we will have these general T many finite many decision stages. And throughout the slides, I will be using this bracket notation to denote the integer set from 1 to T. And in terms of the underlying uncertainty, the stochastic process, let's say how our demands they evolve, we will be using this psi subscript T to denote the random variables associated with our stage T. For instance, if you have 3 different types of products, their demands are assumed to be uncertain, then this is a 3-dimensional vector consisting of these demands of these 3 products associated with stage T. On the other hand, I will be using the superscript notation to denote the history of these random variables, these demands, starting from stage 1 up to stage T. So in other words, if you have observations up to T, then this whole set of observations will be denoted with the superscript notation. In terms of the system dynamics, as we already reviewed, we will get to make a set of decisions, observe the new set of random variable realizations, and we will then move to the next stage and make the next set of decisions. So in that regard, the decisions to be made at this stage T, for instance, our xt, let's say, decision vector, it is a function of the history that we observe up until that point. So in that regard, these decision variables in a multi-stage stochastic program, they are parameterized by these random variable histories up to their associated stage. In that regard, they depend on the history, but they do not depend on, for instance, psi t plus 1 or anything else that you will observe in the future. They are non-anticipative, meaning that they are not depending upon something that you will observe after you make these decisions. So decision variables are that we have in our model, they are themselves random variables, but they are at least non-anticipative. And most notably, our very first stage decisions, X1s, they are to be made before observing any uncertainty at all. In that regard, they are deterministic. So for convenience, you can think of them as parameterized by psi1, which is for convenience fixed 1. So it is constant. So x1 is a decision vector that is deterministic. And in our models, we will look into these difficult version of these multi-stage stochastic programs where we will have some mixed integer decision variables. So some of the decisions to be made, for instance, whether you will set up the production at all or not, they could be like binaries or general integers. We are looking at this mixed integer case. So here's the general form of a multi-stage stochastic mixed integer programming model. And without loss of generality, any mixed multi-stage stochastic program can be brought into this general form. So the objective commonly used is, if you're a risk neutral decision maker, is to minimize the total expected cost. So you look at all the decision stages you have, whatever decisions you made there, you incur their cost, but the expectation here is taken with respect to the whole random variable realizations, the full history, the full sample path. So this is capital T. So everything that will be observed, the expectation will be taken with respect to this joint probability distribution of all of our random variables. So we are trying to minimize this expected total cost subject to 2 different sets of constraints. So for every decision-making stage T and for every possible scenario or sample path, in other words, for every possible realization of this psi superscript T vector, almost surely we would like to satisfy the following inequalities. First of which is called state equations, and these are the ones linking 2 consecutive decision stages together. So specifically, this xt minus 1 decisions are linked to the next ones, xt decisions. So these are the inequalities that are linking our consecutive stages together. On the other hand, the recourse constraints, they are only local, they are only stage dependent, they are only associated with t, they don't mix and match different stage information. And as I mentioned, we might very well have some integer variables. So we are talking about mixed integer setting here. So how we can solve such multi-stage stochastic mixed integer programming models? There are 2 common approaches in the literature, and they are very commonly used. The first of which is this restriction of the underlying stochastic process. So if you have, for instance, these demand type of a stochastic process, then you restrict the demand process in the form of a scenario tree. For instance, here, if for the very first stage you say, oh, for my demand vector, I will only consider 2 options. Let's say if you have, again, 3 types of products, maybe the first option will say that their demands will be 5, 10, 15. The second option will tell us, let's say their demands will be 6, 2, 1. You only consider that many, very limited number of options. But if you would like to get an accurate or at least good enough approximation of the real underlying stochastic process, then you need to have a huge branching factor. 2 wouldn't do the job with justice. And in fact, if you consider increasing the number of decision-making stages, the scenario tree size that you need will actually grow exponentially as such, it will really lead to these computational difficulties to solve these stochastic programming models, even approximately. And by the way, what I mean by a scenario is if you consider a particular realization of the demand process for all the planning horizon, this is what we call a scenario tree, or we also call it sometimes sample path. The existing most commonly used approaches, they, on top of that, usually make further assumptions. For instance, they assume that the stochastic process has this independence, meaning that the demands of one stage has nothing to do with the demands of another stage. They are completely independent. Or they make this other assumption that maybe the randomness only appear on the right-hand side of the constraint. You cannot handle cost or left-hand side type of uncertainties. So there are some efficient decomposition-based approaches for such restrictive settings, but we will follow the opposite approach. Rather than simplifying, restricting the form of the underlying stochastic process, the demand process, for instance, in the form of a scenario tree, we will rather restrict our form of our decision variables, our decision rules. So let me explain what we mean by this decisional-based approach. So let me ignore the integer part for a second, and let me tell you a little bit about multi-stage stochastic linear programming models and the application of these decision rules on the linear setting. So these are called, the most commonly used decision rules are called linear decision rules, in short, LDRs. So what do we do in this LDR-based, linear decision rule-based approach is we restrict all of our decisions to be a function, and specifically a simplified form, a linear function of the observations that are made up to that variable's decision stage. And if you do that, if you make such a restriction on the type of decision policy that you are employing, then this will simplify your problem tremendously, especially it is going to lead to a static, non-adaptive problem. So here's how it goes. So this is representing our original multi-stage stochastic programming model, where remember our decisions, for instance, at stage T, they are functions of the history up to that stage T. Right? So in this linear decisional approach, you say that, oh, you know what, these decisions that were functions of history that could have been adapted based on your previous observations of the randomness, I'm not going to give you the full flexibility. Instead, I will enforce them to have this linear form of the random variable realization. So for instance, here, if this vector is giving you all the demand realizations for all the products up to T, you give a coefficient that is put into this new vector or matrix of variables. So you multiply all the demand observations with their associated deterministic coefficients, and that's how much you are going to set this variable V. For instance, if this xt is representing how much to produce from a product, then you will use the demand observations, multiply them with these constants that you are going to optimize over, and whatever the demands multiply with these constants that you predetermine, this is how much you are going to produce as the blue xt. So if you apply such a so-called linear decision rule on all of your decision variables for every stage, that collapses this huge multi-stage problem into a static single-stage problem, where your new decision variables now here will be these deterministic xt coefficient type of decision variables. So if you are working on machine learning, this is more so like this linear regression type of an approach. And these variables are deterministic, that I will be referring to them as LDR decision variables. So instead of now working with these functional type of decision variables, you will create this finite set of linear, finite set of deterministic decision variables, and accordingly, the single stage problem you will solve to find the best values for them. So this is on the primal side. We were applying them to these X variables, but you could also actually, if you're in the especially linear programming setting, as you know, there's this duality concept, and you can play the same game very well on the dual side. And these are going to lead to these dual decision rules. So if you have this primal, then you can build, especially for the LPs, you can build duals of them. And in that regard, whatever you are going to do on the primal side, for instance, applying LDRs on these primal variables, you can now do the same on the dual side, apply LDR restrictions to the dual variables. Accordingly, you can obtain bounds for your optimization problems. So that's the idea. If my primal is a minimization problem, and if I consider a dual problem, which always gives you a lower bound for minimization problems, even though I further restrict these dual variables to follow a linear decision rule, I will get a valid lower bound on my true optimal objective value. But this was for the LP setting, and it was relying heavily on the LP duality. So what if we are working on the mixed integer setting? Then there's no such thing as LP duality. And moreover, remember my decision rule, I was trying to do something like I wanted this guy to have whatever the realizations that you have times these deterministic variables. I would like these values obtained as a result of my LDR. If I want this variable to be integer with whatever dimension, I need to ensure that I'm going to set these once and for all, but whatever demand values I observe, their formula, this LDR formula, should lead to an integer value. This is too much to hope for. So this could lead to infeasible solutions. In other words, LDRs are not directly applicable in the integer setting. So let's not rely on LP duality. Let's not rely on such primal LDRs then. So our idea is, if you don't have LP duality, whatever exists for integer programming, for instance, a different type of duality, Lagrangian duality, let's use it. And our decision rules will not be applied on the primal side because of this integrality issue. It is very difficult to ensure. So we will be deriving these so-called dual decision rules. So here's the Lagrangian duality if you want to refresh your memory. So on the left-hand side, I do have a primal problem in the form of minimization. So if you would like to do Lagrangian duality, then you pick your favorite set of constraints to be relaxed to obtain the dual, and then you relax them by using these so-called Lagrangian dual multipliers. I'm calling them with this vector lambda, and then you move these guys to the objective. So in other words, when you remove them being constraints from the primal and put them into the objective, you allow them to be violated, but for every unit that are violated, then you penalize them with this Lagrangian multiplier lambda. And the good thing is, if this is a minimization problem, for any non-negative choice of lambda vector that you have, if you solve this dual problem, then you get a lower bound on the optimal objective value. And this is true for every lambda, and this is called the Lagrangian relaxation problem. In that regard, if any lambda gives you a lower bound, if you look for the lambda that gives you the largest lower bound, this is what we call the Lagrangian dual problem. So this will give you the strongest possible lower bound from such a Lagrangian dual. So that will be the key idea. We will apply them to multi-stage stochastic programs now. So our key idea is to use this LDRs, apply them to these lambdas, Lagrangian dual multipliers, and get our bounds and primal policies guided by them. So our idea is to apply these linear decision rules in some Lagrangian dual reformulations of our multi-stage stochastic mixed integer programs. So in that regard, I will quickly show you two different Lagrangian duals that we are proposing. First of them will be relying on the already MSP formulation that I showed you, where we will be relaxing these state equations linking in consecutive decision stages together. The other one is, I will first show you an alternative reformulation of the original multi-stage problem called Nonanticipative dual. And for that one, there will be so-called non-anticipativity constraints, which we will relax in a Lagrangian fashion. So either one of these relaxations, Lagrangian relaxations we will use. Here's our full general framework to obtain primal solutions as well as dual solutions, as such lower and upper bounds on the true optimal objective value of our multi-stage stochastic programs. So our very first step, given a multi-stage stochastic mixed integer program, we will choose one of the two Lagrangian relaxations, and we will decide on whichever Lagrangian relaxation we would like to do. And then accordingly, for their Lagrangian dual multipliers, we will enforce them, restrict them to follow a linear decision. And this will basically take this multi-stage problem, and this application of LDRs on them will collapse them into two-stage stochastic programs. And if you look at the literature, there exists a lot of nice solution efficient decomposition-based solution methodologies for solving two-stage stochastic programs. We will employ them. For instance, specifically, if you have heard of it before, we will solve it again by means of approximations, but specifically employing this sample average approximation, which will require you to get a sample of scenarios from the underlying probability distribution, solve the problem for that sample of scenarios, and whatever candidates that we will get for our LDR decision variables, that will be the solution. But after we get our candidate approximate solution, or the LDR variables describing them, I will show you shortly what they mean exactly, then in order to evaluate in a non-biased way to get statistically valid lower and upper bounds, we will get another sample of scenarios from the underlying distribution. For instance, whatever demand distributions you have, maybe you have multinomial distribution, you will get another sample from that underlying stochastic process distribution, which will be quite large compared to the one that you use in the solution phase. And you will evaluate the true quality of this LDR policy or Lagrangian dual policy. If you put that to the evaluator, that will give you, for a minimization problem, a confidence interval on the lower bound. In other words, if you have this, let's say Z star is a true optimal objective value of the multi-stage problem, we will get a confidence interval which will be statistically valid lower bound. And we will also be able to design some algorithms that will be able to get us some primal solutions. Accordingly, we will be able to get a confidence interval on the upper bound. So we will have both sides, so we can talk about optimality gaps. So let me show you now two of these Lagrangian relaxations and how we enforce linear decision rules to their multipliers. So first of those is called, as I said, Stagewise Lagrangian relaxation. So here I am starting with our original multi-stage stochastic programming formulation. We have the state equations and recourse constraints. And what we will do in this first relaxation is we will relax these state equations by using these Lagrangian multipliers. So because these constraints are for every stage and for every scenario, in other words, every possible history you can observe up until that stage, we will be relaxing them with their associated pi t dual variable, which is a function of this history. So in that regard, you might be thinking that, oh, this is a random variable. This is a functional type of a variable itself. How would you do that? Bear with me for a moment. I will just assume that like I'm given these functional form of the duals. Let me do the relaxation, and then I will apply LDRs to simplify them, and then we will have a much better idea how they will work. So let's say we have these associated duals with our state equations. What we do is we remove these state constraints and rather we push them to the objective. We do the Lagrangian relaxation. So given these Lagrangian dual multipliers, we move this term, we allow violation of these state equations, but if they are violated, we penalize them with their corresponding Lagrangian multipliers pi t. So we move this state equations to the objective. This is our Lagrangian relaxation problem, and for any given choice of Lagrangian dual multipliers, this problem, if you could solve it, you get a lower bound on the true optimal objective value. And as I said, if for any choice of pi, this gives us the lower bound, the best of which will be maximizing this lower bound over our choice of pi's that I will do in the next slide. But before I move on to the next slide, I would like to highlight one thing about solvability of this Lagrangian relaxation problem. So suppose I'm giving those and I'm trying to find the lower bound by solving this problem. One thing that is good about this is once we move these guys to the objective, now we've broken the link between the decision stages. So if you look at the remaining constraints in this Lagrangian relaxation problem, you will see that they are individual set of constraints for every stage and for every possible scenario. So this can be solved by means of actual decomposition. So if you want to solve this Lagrangian relaxation problem, it actually decomposes by both decision stage and the scenario sample path. So you can fairly efficiently solve this Lagrangian relaxation problem. But let's say you solve it efficiently for a given choice of pi's, you get a lower bound. But if you're after obtaining the best lower bound, then you need to find the best choice of Lagrangian multipliers to maximize your lower bound. This is what we call this Lagrangian dual problem. And the value, the lower bound that we will obtain from this is this lower bound coming from this stage-wise Lagrangian dual. But as I said, like these Lagrangian multipliers, these are functions. And in fact, if you look at them carefully, they are functions of the random variables, the history. So these are random quantities themselves. So how can I optimize over them? This is not any easier, if not more difficult than my original maybe stochastic program. So let's simplify them by applying linear decision rules. So take this Lagrangian multiplier, which is this random variable as a function of the history. Let's restrict them to follow a specific form of a linear decision. So in that regard, these beta t's will be my deterministic, what I was going to refer as this LDR decision variables, bunch of coefficients that I will optimize over. And here I am using this as the function of the history. I'm using something a bit more general than what I just told you before. In the previous version, I just told you something like star superscript t times beta t, where this was the directly the history, let's say demands whatnot that you had observed up until this point. Now I'm using some different functions of the history, the demands that I observed, and these things are called basis functions, so that I have a little bit of more flexibility. So what basis functions do is, given a set of random variable observations, xi superscript t, they return me a bunch of numbers. So here's an example. So for instance, let's say I'm considering a decision variable at stage 3. And in that regard, I'm trying to give you, let's say, pi 3. What should it be? So what I'm saying is it depends on what type of predetermined basis functions you are using. Let's say for stage 3, I'm using these basis functions, first of which is a constant, so that they become actually affine, not linear functions. And let's say this is the second stage random variables and third stage random variables. So this is exactly what I showed you before. I am using the random variables themselves as the basis functions, which are called standard basis functions. So then I'm saying that this pi 3 variable, which is a function of this xi2 and xi3 and the constant, it cannot take any value, but it will take the observations of these random quantities, xi3, xi2, and 1, and it will multiply them with these deterministic variables, and these are going to be our new decision variables, LDR variables. But the basis functions will allow us a little bit of more flexibility. For instance, I can say, oh, in addition to these basis functions, I'm defining a fourth one, which will multiply, let's say, demand from stage 2 and demand from stage 3. Accordingly, I will add another term here, and I will give you another decision variable. So as you add more decision variables for basis functions, you are adding more and more flexibility to your decision rule. But of course, you are adding more and more decision variables. It might get too difficult to optimize, so you need to find the nice sweet spot. All right, so if I do this LDR restriction, so I restrict my Lagrangian dual multipliers as a function, linear affine function of the basis functions of the history, then I now have to optimize over these deterministic coefficient LDR variables, betas. And if we do that, then we obtain this restricted version. I will not be able to find a lower bound as high as before. I'm restricting my dual problem, but nevertheless, this problem I can solve fairly easily compared to the original one. At least I can get a valid lower bound. So the second one, I will just briefly tell you the idea. I won't be able to get into much details, but we will apply the same game plan, but on a different reformulation of the original multi-stage stochastic program. So starting with different type of decision definitions for this reformulation, namely, I'm going to introduce these so-called perfect information variables. So instead of xt, which was a function of the history, small t up until that point, I will define these variables y's that are functions of the full demand process that is observed psi superscript t, the full length of the planning horizon. So I will define these information variables, which are functions of the full sample path observations. So these variables are actually then, they are not non-anticipative, they are anticipative, and accordingly they will have this capital YT, their anticipative feasible region. And then you can reformulate the multi-stage problem by using these new anticipative variables with their associated constraints. But in order to ensure that the decisions are nevertheless are non-anticipative, they cannot depend on the future, they should depend only on the history that they are functions of, we add these so-called non-anticipativity NA constraints, or that are going to ensure this consistency and enforce this non-anticipativity. So these constraints, what they're saying pretty much is, if you're at stage t, then if you're talking about this decision variable vector associated with stage t, then given the history, if this is the history that you observe, but there could very well be some other scenarios that you are considering for the future, as long as the history is the same, it is fixed to this psi superscript t, these decisions should be the same. So in other words, if you think of like, this is a demand path that you observed and you are here at stage t and you are trying to decide on what to do about these YT decision vector, irrespective of the future, if your history is fixed to psi t, if it is the same, irrespective of what else you will see after that point, you are supposed to make the same set of decisions. So they should take the same values, they should be non-anticipative. So in other words, these are ensuring this non-anticipativity. The rest of the formulation became anticipative, and these are complicated constraints. So we are going to go ahead and relax them in a Lagrangian fashion. So for each of these constraints, we define a Lagrangian dual multiplier, and we will remove them and push them to the objective to obtain this second optional Lagrangian relaxation. So if you do that, if you solve this problem for any choice of Lagrangian multipliers, you will get a lower bound. And another good thing is this also decomposes if you want to solve this relaxation problem, but only by scenario, not by both stage and scenario. And the best of the lower bounds from this relaxation, again, will require you to solve this Lagrangian relaxation, Lagrangian dual problem to find the best set of multipliers to get the strongest lower bound. But this is a difficult problem to solve because these Lagrangian dual variables, multipliers, they are random quantities themselves. So simplify it by applying a linear decision rule on them, just like before. And now you can solve this restricted version of the Lagrangian dual problem because these decision variables, LDR variables, they are deterministic. They do not depend on any randomness. So if you put all these things together, we have proposed these two different Lagrangian duals, namely Stagewise and Nonanticipative dual. And for the restriction of the relaxation of the constraints, we relaxed here the state equations. Here we look at the alternative non-anticipative formulation from which we relax the non-anticipativity constraints. To obtain relaxations are here. It decomposes by scenario. Here you have on the left-hand side double decomposability. So this is an advantage over the non-anticipative dual. So where is the catch? Of course, there's no free lunch. What we can prove actually is that, so this is the advantage of the Stagewise dual, this potential, the faster solvability, but in terms of the lower bounds that you will get, the non-anticipative dual, we can prove that it is actually stronger. So the theorem says a little bit something more detailed. So specifically, if you actually predetermine these set of basis functions for the Stagewise first dual, then if you give the fair chance to the second dual, if you determine the basis functions in such a way, then you can get a better lower bound from the non-anticipative dual. So it is technically stronger. It cannot be worse. All right, so this is the relaxation part. And as I said, if you use either one of these Lagrangian relaxations and apply this LDR rule, and you can obtain this two-stage version of the restricted dual problem. If you solve it, however you solve it, we use sample average approximation and a decomposition cutting plane algorithm. Either duals, you will get these LDR decision variables. I believe I was calling them alphas and betas. Alpha is for the Stagewise dual, beta is the, let's say, LDR variables for the other dual. So whatever you do, you solve the obtained Lagrangian dual restricted problem to get the LDR decision variables. And if you generate another potentially huge sample to see their actual value, you get your lower bound. But that's not the end of the story. We can do something even better than that. So after getting these deterministic decision variables, either alpha or beta LDR decision variables, we could also use these LDR dual variables to guide some primal algorithms so that we get an actual implementable policy in practice, as well as a result of which an upper bound on our true optimal objective value. So if I tell you like the general idea behind this primal policies in real life, in practice, what do? So you do the following. You apply these policies in a rolling horizon or folding horizon fashion. So at each stage, let's say, whatever tool that you are using to make the decisions, at t-1, the tool suggested you to implement, let's say, x set of t-1. And up until that point, you had observed these random variables. And as soon as you commit and implement the production plan or inventory management decisions, at that point, t-1, you get to make the next set of observations, let's say demands associated with the next stage. And by using this previous decisions that you committed and the revealed observations of the uncertainty, you need to again call your tool of decision making and get to make your stage T decisions. So whatever policy you design is gonna describe you what goes into this box. So how would you be able to make the decisions? This is what we have some design choices to make. So in terms of what goes into this box, in terms of especially considering this under uncertainty setting, you could choose to ignore completely the uncertainty about the future that you are faced against, and you can employ a myopic policy there. So you say, I don't care anything that comes next, I don't care about any uncertainty associated with the future. I will do the best choice that I can do with my current information. You completely ignore the future, which will lead to this myopic policy, which is usually quite suboptimal. So if you want to take the future into account, but in a simplistic manner, then you can try to put this expected upper bound policy type of a tool into this decision-making box. So in this expected upper bound policy, you will say, look, I will care about the future here. But instead of considering many demand realizations for the future, I will literally consider one possible path towards the future, where I will say, if I'm at this point and I have these observations up until this point, condition on the fact that whatever demands, random variables that I have for the future, I will find their expected value, and I will take the single scenario towards the future, which is the expected, conditional expected values of the demands that you have. And you optimize current stage decisions by considering this single expected scenario towards the future. So this will be one of our benchmarks in our numerical experiments that I will present shortly. But we can do something better with our LDR decision variables. So if I'm here, what I can do is I can guide, for instance, this policy. I can modify this optimization problem by using these alpha or betas LDR decision variables. In other words, I can use my LDR dual solution to provide some guidance to make my decisions. And this is the solutions that we will compare against this benchmark expected upper bound policy. So I will, we actually done currently 4 different applications of this Lagrangian decision rules in the stochastic, multi-stage stochastic setting. I will briefly show you the application domains and a bunch of results where I will just show you in terms of lower and upper bounds, and most notably the optimality gap between the two, how much we can improve compared to the traditional bounding techniques for multi-stage stochastic programs. So the first one is multi-item lot sizing problem. The main decisions are how much to produce, for instance, for each type of product. In other words, determine the lot size, and accordingly, you should decide these binary decisions whether you will set up the production for each item at all or not. But the demand will be the main source of uncertainty, and it will be revealed to you gradually over time, according to which you need to do the inventory management, update the inventories, as well as if you allow the backlog. So here, what I'm showing is this. If you use the traditional lower and upper bounding techniques, I don't have time to get into details, but perfect information is a commonly used in multi-stage stochastic programming method to get a lower bound, and this conditional expected upper bound policy will give us the upper bound for our cost minimization problem. So if we use these existing commonly used generic techniques from the literature, we obtain for a variety of instances here such an optimality gap, the gap in percentages between these bounds. For instance, we can see that the gaps could be as high as like 50-something%, and they are significantly large. So if we compare this gap with the gap that we obtain by using our stronger dual, non-anticipative dual, but in terms of the primal policy, the other one, first one, SW, stage-wise dual guided policy, primal policy was giving us a better upper bound. So we get the best of our ideas for lower and upper bounds and obtain an optimality gap using our own bounds. And we see how much of this existing optimality gap we close. So here in the second graph, we are showing the gap reduction over the existing gap. And we can see that like there could be these as high as 80%, but definitely 20-40% gaps of the existing one we are closing with our novel bounds. So the second problem, I don't have time to get into details of the description, but it is a resource allocation problem in telecommunications area, which is called routing and wavelength assignment. So given a network, telecommunication network, which is consisting of these nodes and fiber links, you have a bunch of traffic requests. So you need to give a connection, grant a connection, for instance, from node 1 to node 6 or node 2 to node 8. So you have these pairs of nodes as traffic connection requests. And how you can grant a request is you need to choose a path. Let's say if you want to send something from 1 to 6, you not only need to choose a path from 1 to 6, but also a wavelength. I'm showing them with colors, which is called the combination of a path and a wavelength. The color is called a light path. So this is by choosing a light path, you can grant a request. And there are certain constraints, of course, in the problem. A light path assigned, actually, it cannot have a common wavelength on each link it traverses, or light paths with the same wavelength, they cannot share the same link. For instance, if you want to use this particular link 1 to 3, you cannot use it with 2 different paths of the same color, so on and so forth. And the goal is to maximize the expected number of course, there is traffic uncertainty. Demand will be the main source of uncertainty. You want to maximize the number of requests that you granted. Again, forget about all the numbers, just look at the highlighted ones. What I'm showing is for certain options, variety of instances, variety of basis function options, whatnot. Again, I'm showing you the same measure here. How much of the existing initial gap you obtain by the traditional techniques we can close with our bounds. You can see that we have significant savings in terms of the optimality gap. The third application, again, very briefly, is from the healthcare area, operating room scheduling. So you have in Toronto, for instance, here you have these 3 hospitals that are sharing their pool of patients and according to their operating rooms. So they want to make a common schedule so that they can improve the efficiency. So in that problem, what you need to decide is for each day of the planning horizon, which hospitals to be basically to spare for this operation and which operating rooms to open for each day, and accordingly how to assign these patients to these open or operating rooms. And if the surgery durations are taking longer than what you expected, you might need to reschedule some people, or in the worst case, you might need to push them to the next planning horizon, for instance, next week. And the goal here will be to maximize overall the benefits from the surgery completion and the cost associated with this. We again apply for very simplistic instances. This is an ongoing work. These are preliminary results. But again, compared to the existing initial gap, our gap reductions through the decision rule-based approaches is significant. The final example, I'm going to skip the description. You must be familiar with the staffing and general scheduling problem, for instance, in call centers. For some call center application examples here, again, we see that in the last column here, we have significant gap reductions. So in just a couple slides, I also would like to give you the spoiler about our upcoming work, which will be hopefully online next month. We also apply these Lagrangian dual decision rules along with some other recently proposed decision rules to the robust optimization setting, specifically this difficult problem class of multi-stage adjustable robust optimization setting, where the options methodologies are quite limited, to be honest. So as I mentioned before at the beginning, why you might prefer the robust optimization, either you might be lacking the knowledge about the underlying stochastic distribution, or you are maybe more of a conservative decision maker and you want to optimize the worst case of your decision-making objective. So in terms of the model, it looks pretty similar, except the fact that the objective is now optimizing the worst case cost, for instance. So here the Z is representing the worst case cost, and for every scenario, whatever costs happen, you are trying to be finding the worst of these costs. So this is the multi-stage version of the adaptive robust optimization model. So in this upcoming work, what we do is, for the dual side, we are again borrowing this idea that we had, Lagrangian dual decision rules, to obtain a lower bound on the true optimal objectivity of the robust problem. Here we don't have these dual guided decision rules, but we are borrowing from the recent literature these direct primal decision rules called two-stage decision rules to obtain primal implementable policies and accordingly upper bounds. And this new decision rules are allowing us to develop some methodologies, of course, to solve these either primal or dual restricted problems. So for different setups, for instance, depending upon the uncertainty set version and continuous or mixed recourse, we have different methodology suggestions. All right, so I will just leave the summary slide here and I will stop here for the sake of the time. Thank you very much for joining us today. And if you have any questions, any ideas, anything you want to discuss, I will be more than happy to stick around.